You're listening to DTFHN for April 19th, 2026. I'm your reverse-engineered host, Jack Haxman. We are your daily tech feed for Hacker News, a website where people who build things argue about how things are built. Today's got that particular energy where everything you thought was simple turns out to be lying to you. Let's crack it open. Let me work with what's available from the title and comments to write this segment. Can every transducer betray you? There's a question in physics that sounds like a riddle but isn't. If a speaker turns electricity into sound by vibrating a diaphragm with a magnet and coil, what happens if sound vibrates that same diaphragm in reverse? The answer is it generates electricity. It becomes a microphone. The physics doesn't care which direction you're going. It's the same mechanism, just run backwards. This is the kind of principle that musicians have known forever. DJs at live shows will grab their headphones, plug them into a mixer's mic input, and shout into the driver when they need a stage mic in a pinch. Rockbox, the open-source firmware for portable music players, actually shipped a feature letting you record voice notes through your regular earbuds. The hardware was already capable. Someone just had to write the software that said so. What the researchers behind SPEAKE did was take this parlor trick and turn it into an air-gapped exfiltration channel. They demonstrated that the Realtek audio codec chips found in practically every motherboard can silently reassign a speaker output jack to function as a microphone input. At the software level, no physical access required beyond the initial compromise. No hardware modification. The computer's own speakers become listening devices. Even on machines where microphones have been physically removed or disabled as a security measure. Think of it like architecture. You build a vault with no windows. Seal every opening. But the walls themselves are made of glass. You forgot was transparent. The transducer physics means the attack surface was always there. It was built into the silicon. The craft here deserves admiration. This is elegant patient security research. They mapped the codec's register level behavior, found that the jack retasking feature in Realtek's HD audio spec could be exploited programmatically, and proved that usable audio, enough to capture speech, enough to encode and exfiltrate data, could be picked up through connected speakers and headphones functioning as improvised microphones. The distances weren't enormous, but they didn't need to be. In an air-gapped facility, the threat model is the room itself. What makes this genuinely important is what it reveals about assumptions. Every secure facility that strips microphones from machines but leaves speakers connected has been operating on an incomplete model of the hardware. The physics was never on their side. A magnet in a coil works both ways. And now there's a proof of concept published in the open at Untitled, where anyone can study it, defend against it, and build better security models because of it. That's how the ecosystem is supposed to work. The vulnerability existed whether or not anyone published. The defense only exists because someone did. So what happens when you take 50 years of computing history and just give it to everyone? In September 1975, a magazine called Byte hit newsstands with a cover price of $1.50 and a thesis that would have sounded absurd to most of the computing establishment. The thesis was this: computers belong to individuals, not departments, not institutions, people. At the time, the entire personal computer industry was a handful of hobbyists soldering kits in garages. Byte treated them like the vanguard of a revolution. It was right. Now, every issue, starting from that first one, is sitting on the Internet Archive, freely accessible to anyone with a browser. And this is worth pausing on, because what you're looking at isn't just a magazine archive. It's the primary source material for one of the most consequential technological transitions in human history, preserved in the open where anyone can study it. Pull up that first issue from September 1975. You'll find articles about building your own computer from scratch. Not configuring one, building one. The authors assumed you had a soldering iron and a willingness to learn. They published full schematics, full source code, full theory. The magazine was essentially an open source repository before the term existed. A monthly distribution of knowledge designed to put capability directly into readers' hands. What Byte captured, issue by issue, was the moment computing stopped being a priesthood and became a craft. You can trace the entire arc. The early issues are hardware-obsessed, because software meant toggling switches. By the early 80s, you're watching software eat the conversation. By the 90s, networking, the whole trajectory of personal computing, is there. Told not by historians looking backward, but by practitioners writing in real time. The comment from a reader who remembers JP's writing while, as they put it, monkeying on newfangled machines. That's the texture you only get from primary sources. These weren't abstractions. These were people figuring things out with their hands. And the fact that this archive exists on the Internet Archive, not behind a paywall, not locked in some publisher's vault, matters enormously. This is the documentary record of how computing became democratic. The tools, the schematics, the arguments, the letters to the editor. All of it searchable, downloadable, remixable. The same principles Byte championed in 1975. Open knowledge, individual empowerment, the right to understand and modify your own machines. Are the principles keeping this archive alive 50 years later? The thread runs unbroken. Now for something completely different. Ever wonder what actually happens under the hood when you hit pause? Every game you've ever played is lying to you about time. When you hit pause, you expect the world to stop. Simple, right? The clock freezes, everything waits, you come back, it all picks up. But here's the question nobody asks. What is everything? Because a modern game isn't one system. It's dozens of systems, running at different rates, talking to each other through shared state. And stop is not a concept any of them were designed around. Let's start from the constraint. A game loop is a function that runs 60 or more times per second. Each tick, it reads input, updates physics, moves entities, resolves collisions, renders a frame. Pausing means you need every one of those subsystems to agree on what stopped means. Physics needs to stop integrating forces. AI needs to stop making decisions. Animation needs to stop advancing. Audio needs to, well, does it? Do you want the music to keep playing? Do you want ambient sound? Already you're making design decisions disguised as engineering decisions. The common approach, and you'll see this in every game jam engine, is a timestamp variable. Set it to 0. Multiply all your updates by delta time. 0 times anything is 0. Done. Except it's never done, because some engineer somewhere divided by delta time instead of multiplying, and now you've got a division by 0 crash hiding in a particle system that only triggers when you pause during a specific explosion. The comedy writes itself. One of the best examples comes from Super Mario Sunshine. Pausing that game misaligns the collision system, which runs 4 times per frame, with the main game loop. The result is that certain physics interactions behave differently depending on whether you paused at the right moment. Speedrunners exploit this. A pause button, the simplest possible input, becomes a tool for breaking the game's reality, because 2 clocks fell out of sync. The old Quake engine took a different philosophy entirely. Its demo system was deterministic. Record the inputs, replay the inputs, get the same result. That only works if time is a value you control completely, not something you're borrowing from the operating system. The engine owned its own clock. That's elegant. That's also the kind of architecture you only get when one person understands the whole system. This is why open engines matter. When Inlinked Software released the Quake source, every game developer on Earth got to see how deterministic time works. Not a paper about it. The actual code. That's knowledge compounding at the speed of copying, and every modern engine builder since has carried those patterns forward. The pause button is trivial until it isn't, and when it isn't, you want to read how someone else solved it. Elegant data structures are a lot like elegant game engines. Now pause, you don't appreciate the design until you need the performance. One commenter on this piece dropped a line that stuck with me. Quote, "In the age of agentic programming and the ever-increasing pressure to ship faster, I'm afraid this kind of knowledge will become more and more fringe." They're talking about skiplists. A data structure most working programmers have heard of exactly once, in a textbook, and then never thought about again. And honestly, that commenter might be right. But Will Wilson at Antithesis just demonstrated exactly why that would be a tragedy. The setup is beautiful in its specificity. Antithesis runs your software thousands of times with different faults injected, building a branching tree of timelines. Every path a different sequence of choices the fuzzer made. They needed to query that tree, walk up from a log message to the root, reconstruct the history. Simple, right? Except the data was massive, so it lived in BigQuery, and BigQuery is an analytic database. It's built for scanning everything in parallel, computing aggregates. What it is emphatically not built for is point lookups. Walking a tree one parent pointer at a time means one full table scan per step. That's O of depth reads across your entire dataset on an analytic database. Let that. Actually, no. Just imagine your cloud bill. The solution was a generalization of skiplists applied to trees. Skiplists themselves are elegant. Linked lists with express lanes, each level having the nodes you need to check, giving you login search instead of linear. Wilson and his team took that idea and extended it to tree structures, letting them skip up ancestor chains the same way a skiplist skips along a sorted sequence. The comment section split predictably, one camp pointing out that B+ trees beat skiplists on real hardware because of cache locality and pointer chasing, another noting the Redis's sorted sets. Probably the most widely deployed skiplist in existence. Proved the structure earns its keep in the right context. Someone linked a paper on SMD-friendly skiplist algorithms for GPUs. The data structure hipsters showed up in force. But here's what actually matters. Wilson wrote this up, published it on the company blog, walked through the problem, the dead ends, the generalization. This is builder culture at its finest. Someone solved a genuinely hard problem and then put the blueprint, put the solution where anyone could find it. 1,000 engineers reading this post now understand a technique that took Antithesis years to develop. That's knowledge compounding at the speed of publishing. The commenter worried about data structures becoming fringe has it backwards. They become fringe when people stop writing posts like this one. The antidote to institutional knowledge loss isn't slowing down. It's writing it down in public where the next person who hits the same wall can find it. 5 stories in, and we haven't even gotten to the physicists yet. Let's fix that. A material called Tantala takes in one color of laser light and puts out every color of the rainbow. One input, full visible spectrum plus infrared out the other side. That sentence sounds like it belongs in a fantasy novel, but it's a real result, published this week in Nature by a team at NIST. The problem they solved is deceptively simple to state. High-quality compact lasers exist for only a handful of wavelengths, If you need 980 nanometers, you're in luck. Semiconductor lasers do that beautifully. If you need the specific wavelength to trap a convolus woe, we crap a breed of palm was repashably other the size of a filing cabinet that drinks kilowatts and costs more than your car. Quantum computing and optical atomic clocks have been lab-bound, not because the physics doesn't work, but because the light sources are furniture. What Pap, Brodnick, and their collaborators built is a photonics chip. A layer cake of silicon dioxide, lithium niobate, metal control elements, and tantala, all deposited onto a standard silicon wafer using fabrication techniques borrowed from the electronics industry. The lithium niobate shifts colors. The metal interfaces switch light on and off at data processing speeds. And the tantala layer does the thing that matters most. Broadband nonlinear conversion from a single pump wavelength to essentially arbitrary output. Follow the logic all the way through. If you can fabricate these on standard silicon wafers, you inherit 60 years of semiconductor scaling. The same economic engine that put 1 billion transistors on a chip for a few dollars starts working on photonics. Lasers that currently cost tens of thousands of dollars and fill an optical table become features on a chip you can hold between your fingers. One commenter pointed out the implications for ion trap quantum computing specifically. The wavelength you need depends on which ion you choose, and most setups require multiple wavelengths simultaneously. A chip that can generate arbitrary wavelengths from a single pump laser collapses an entire optical bench into a component. This is NIST. The research is public. The fabrication techniques are documented. The tantala deposition process they developed works at low enough temperatures to be compatible with existing chip material. That's the quiet engineering breakthrough buried in the paper. They didn't just demonstrate a capability, they demonstrated a capability that other labs can reproduce on equipment that already exists, using processes that don't destroy the layers underneath. The path from any wavelength on a chip to quantum technologies outside the lab just got measurably shorter. We talked about measuring what matters earlier. Well, let's measure something closer to home. Claude's own token efficiency. Let me be fair to Anthropic for a moment. When you release a new model, you want it to be smarter. Smarter often means more context, more reasoning, more tokens flowing through the system. If Opus 4.7 genuinely thinks harder about your problems, then yes, it will consume more tokens. That's not greed. That's physics. More computation costs more. The counter-argument to the community's frustration writes itself. You're getting a better model, and better models aren't free. Now let me tell you why that argument collapses. In 1995, Microsoft shipped Windows 95, and it was genuinely better than 3.1. It was also genuinely hungrier. Boom! For RAM, for disk space, for CPU cycles. And Microsoft's answer was the same one Anthropic is giving now. Better costs more. But the history of computing since 1995 has been a relentless march in the opposite direction. Moore's law didn't just make chips faster, it made the same work cheaper. The expectation that each generation does more with less isn't entitlement. It's the fundamental trajectory of the entire industry. Bill Chambers built a community tool that lets people anonymously compare token consumption between Opus 4.6 and 4.7 on identical inputs. The data shows 4.7 consuming measurably more input tokens. One commenter ran through their 5-hour usage limit in 2 hours. Another compared the experience to casino design. Intermittent reinforcement optimized to keep you spending. That casino comparison deserves a straight take. When your pricing model is opaque, when token consumption varies unpredictably, when users can't budget their work. You've built a system that profits from confusion. Whether or not that's intentional, the architecture produces that outcome. The deeper issue is that this data exists because someone outside Anthropic built a tool to measure what Anthropic doesn't publicly benchmark. The community is doing its own quality assurance on a closed system, reverse engineering the cost structure of a product they're paying for. That's the tell. When users have to build external instrumentation to understand what they're being charged for, the relationship between provider and user has inverted. The users are auditing the vendor. The tool is open, the leaderboard is public, the data is community contributed. That part, at least, is working exactly as it should. Moving on. I once spent 3 weeks debugging a system where the abstraction layers had gotten so deep that nobody on the team could trace a request from input to output without consulting 4 dashboards. When we finally ripped out 2 middleware layers and made the data flow visible, the bug was obvious. It had been obvious the whole time. The tooling was hiding it. Which brings me to a German professor at Cornell who hands out manual typewriters once a semester and tells her students to write without spell check, without translation tools, without a delete key. The framing in the press is predictable. Analog nostalgia defeats AI cheating, but that framing is wrong, and the actual story is better. Here's where I want to play devil's advocate. The obvious reaction from a pro-technology position is to call this Luddism. Students banging on 50-year-old machines to avoid engaging with the most powerful writing tools ever built. Ridiculous, right? Except listen to what the students actually said. One computer science major, not an English lit student, a CS major, observed that the difference wasn't the typewriter itself, but how it changed his interaction with the world around him. No notifications, no tab switching, no ambient noise from the entire internet competing for his attention. The constraint produced clarity. This is something every systems engineer recognizes. Constraints are not the enemy of good work. They're often the mechanism of good work. The typewriter isn't anti-technology. It's a debugger. It strips away the abstraction layers and forces you to see what you actually know versus what your tools know for you. That distinction matters enormously when you're learning. The real craft appreciation here belongs to Phelps, the instructor, who understood something subtle. She's not fighting AI. She's instrumenting her classroom. She found a way to measure the gap between what students can produce with full tooling and what they can produce with none. And she's using that delta as a teaching signal. One student didn't know why the key is called return. Now she does. Sometimes you have to touch the carriage to understand the abstraction. The best tools are the ones you understand well enough to set down. And what happens when you trace that instinct? Pause, understanding the machine beneath the abstraction. Pause, back 60 years. Story 8. It looks like network access is being blocked by permissions. Let me work with what I have from the title and HN comments to write this segment. Based on the article title, the reader comments, which contains substantial technical details, and the blog's known style, Ken Scherf's Writo.com. I have enough context to write this segment. Buried in the comments on this one is a line from 1963. A digital computer was expensive, slow, and less reliable. That date matters. 1963. The engineers building the B-52's Star Tracker navigation system looked at digital computers and said no, too fragile, too costly, too slow for the job. Instead, they built an electromechanical angle computer. Gears, cams, synchros, and servo. To solve spherical trigonometry problems in real time at 30,000 feet while tracking individual stars through a sensor window. Pull this thread for a moment. The astro tracker needed to know approximately where a star would be before it could point its sensor. That means the system was solving the inverse problem. Given our latitude, our heading, the time, and the star's celestial coordinates, compute the expected altitude and azimuth. Then slew the optics to that patch of sky. Spherical trig, cosines of declination multiplied by cosines of our angle. The kind of math that fills a page of equations. And they implemented it in metal. This is where the craft gets beautiful. The lineage traces straight back to naval fire control. Those World War II gun directors that computed ballistic solutions for moving ships shooting at moving targets. They were the ancestors, the same engineering culture that figured out how to mechanize trigonometric functions with shaped cans and differential gear trains, handed that knowledge forward into Cold War avionics. The I/O was entirely electrical. Synchro signals in, synchro signals out. But the computation between those boundaries was mechanical, gears meshing at precisely machined ratios to multiply angles, cams shaped to the curve of a sine function, differentials summing rotation. What strikes me is the reliability argument. These engineers chose mechanical computation because it was more dependable than digital. Every gear tooth was a known quantity. No bit flips, no memory errors, no software bugs. The failure modes were physical, observable, and predictable. You could inspect a cam with your eyes. Try that with a register. And here's the engineering due diligence that matters. Every component was knowable. The system was, in the deepest sense, open to inspection. You could disassemble it, measure it, understand it, rebuild it. The documentation wasn't an abstraction layer on top of hidden complexity. The documentation was the machine. That's a property we've largely traded away, and it's worth noticing what we gained and what we lost in the exchange. One commenter captured it perfectly. They envied engineers who got to build celestial navigation systems and first-generation fighter avionics. And then added, "Here I am fighting YAML." There's something honest in that. The problems got less beautiful even as the tools got more powerful. But the craft is still there, if you look for it. Ken Shirriff's takedown proves it. Someone is still reading the gears. We talked earlier about designing for the future. Well, here's a case where the future showed up differently than planned. What if the design everybody loves to hate was actually the right answer? Just to a question nobody was asking anymore. Avery Pennaroon, who you might know as the CEO of Tailscale, wrote this piece back in 2017 after attending his first IETF meeting, and it's become one of those essays that keeps resurfacing because the core insight ages like good whiskey. The argument isn't that IPv6 failed. The argument is that IPv6 was a perfectly rational design for a world that never arrived. Run this forward from the early 90s. You're designing the next internet protocol. Every device will have a globally routable address. NAT is a temporary hack that will die any day now. Firewalls are an aberration. The network is transparent end-to-end, the way God and Vint Cerf intended. In that world, IPv6 makes gorgeous sense. Stateless auto-configuration. Addresses derived from MAC addresses. No need for DHCP. No need for NAT. It's elegant. It's correct. Except NOT didn't die. NOT became load balancing. NOT became security policy. NOT became the entire architecture of cloud computing. The temporary hack turned out to be what everybody actually wanted. Not because it was beautiful, but because it solved problems the purists refused to acknowledge existed. And here's the comedy. The IPv6 true believers kept designing for the world that should have been, while the rest of us kept duct taping IPv4 into the world that was. Decades of this. The IETF meetings Penn attended were still full of people certain that adoption was coming, any day now. Penn went on to build Tailscale, which is basically the logical conclusion of his own essay. Stop fighting the net. Stop waiting for the pure network. Just build an overlay that gives you what you actually need. Open source. Works today. That's bootstrapism. You don't wait for the perfect protocol to be adopted by committee. You ship the tool that solves the problem and let people reach it. The lesson here isn't about IPv6 specifically. It's about what happens when you design for the world you wish existed instead of the one you're standing in. The best engineers aren't the ones with the most elegant abstractions. They're the ones who look at the mess, really look at it, and build something that works anyway. Moving on. In 1993, Microsoft shipped Windows 3.1 with a promise that your existing DOS programs would keep working. They mostly did. That backwards compatibility obsession became Windows' superpower and its curse. Layers of shims and compatibility hacks stacked like geological strata, each one preserving some ancient program nobody remembered writing. Unity chose a different path. They chose to molt. A snake sheds its skin in one clean piece. Unity sheds its skin like a sunburned torch. In patches over years, with some bits still clinging while new bits are already flaking. A game developer named Jack Pritz just documented what this looks like in practice. He built a small game called Gun Rocket in Unity 4.6 back in 2015. A month of work, 100 levels. It shipped on Steam, made real money, and then, one day, it simply stopped launching. No error, no log, just silence. What follows is a guided tour through a decade of engine churn. Version 5.5 won't even open because the license check predates Unity Hub. The jump to 2017 breaks the physics. The jump to 2022 deprecates the entire GUI system. Every few versions, some API that was the officially blessed way of doing things gets quietly shoved into a legacy namespace. The game works the whole time, mind you. Once you find and fix whatever load-bearing function got renamed this cycle. The comments are revealing. One reader points out that 2022.3 is still the safest bet if you want your tools to behave. Another notes that Unity's problem isn't churn exactly. It's that they fail to ship anything significant while still managing to break what worked. This is a proprietary engine doing what proprietary engines do. Your game, their platform, their timeline. When Godot breaks something, you can read the commit, understand why, and fix it yourself. When Unity breaks something, you file a ticket and wait. Pritz spent weeks on this migration. The game is a single-screen arcade shooter. Imagine what this looks like for a studio with 1 million lines of code. The tools exist to build games without asking permission from a company that changes its pricing model every 18 months. More people should use them. This has been your daily tech feed for Hacker News for April 19th, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voiced by Quen3 TTS. Not affiliated with Hacker News or Y Combinator. Now go build something you'd be proud to explain from the ground up. We'll see you back here tomorrow.